Section 6.3 exponential functions. It's a continuation, so it's 6.3b of what you've already done. Just some more practice with graphing these exponential functions. So it says graph f of x is equal to 2 to the x minus 1 and determine the domain, range, and horizontal asymptotes of f. So when we're graphing this, if I'm going to graph the parent function of this in red. So let's see, I'm going to use, so get sketch. We've got, put some, just a rough sketch of this graph here. And like I was saying, I'll do the parent function in red. The parent function of this is 2 to the x, so if I think of it like y equals 2 to the x, there's 3 points I always know. I know -1 and 1/2, so that's going to be right about there. I know 0, 1 is right there, and then 1, 2. Those are 3 points that are always going to be true. And then this graph is going to have, I know for the parent function, when this number, or when it looks like this, from exponentials from the previous one, it's going to have horizontal asymptote at y equals 0, so it's going to approach that x-axis but never actually touch it, and then it's going to look something like that for a parent function. This actual function here is, if I recall back all the way to section 3.5, this one is almost identical. We have the 2 to the x, that's the same exact part, but then everything that comes out of this part right here is -1. So everything is shifted down 1, meaning all the points are shifted down 1. This point is going to be shifted down 1 to there. This point is shifted down 1 to there. This point is shifted down. All those points are going to be shifted down 1 unit. And that's what that -1 does. So if you have a plus or minus outside of everything, it's going to either shift the graph up or down. Well, once I have that rough sketch of the graph, the domain for these, there's no roots and there's no variables in the bottom. So the domain in interval notation can be anything, -infinity to +infinity. The range, how low does this graph go? The range never is going to go below the line y equals -1. That's the horizontal asymptote. The original horizontal asymptote was y equals 0, but everything is shifted down 1. So now the new horizontal asymptote is y equals -1. That goes on to answer this last part, but that means as x's get really, really large, in this case approach -infinity, this graph is only going to approach -1. It's never going to actually equal -1. So the range is from -1 and the graph just keeps going higher and higher. It's an increasing graph. So from -1 to infinity. This one here, graph 3 to the -x plus 1. So again, if I draw my graph, put some sketch marks on there. 2, 3, 4, 5, 6, 1, 2, 3, 4, 5. Just to kind of get a rough idea of what's going on. If I draw my parent function in red again, so my parent function is kind of like this. The parent function is going to come from 3 to the x. There's some points that I know 0 or -1, 1/3. If I plug -1 in for x, I know 0, 1, and then I know 1, 3. And then it's going to have a horizontal asymptote again on the x-axis, and it's going to look something like that. That's my parent function. Well, what does the actual function we're asked to graph look like? That's the f of x is equal to 3 to the -x plus 1. What does this plus 1 do? Well, it's outside of everything else, so this plus 1 is going to shift everything up 1. So that plus 1 shifts everything up 1. What does this minus do in front of here? Everything else is the same, except there's a minus in front of the x. That minus, what that does is it changes the x's, or it reflects it. So this is a reflection across the y-axis. And again, that's coming from section 3.5. So that minus x is going to be a reflection across the y-axis, meaning we had a point here. It's going to get reflected across the x-axis, so it's going to go over to here, and then up 1, right there. This point reflected across the x-axis, it can't go anywhere, but then up 1 goes to there. This point reflected across the x-axis, up 1, it's going to go there. And the same with all the other points. We reflect them across the y-axis, so reflect them across y-axis and then up 1. I think I was saying x-axis, but you want to reflect them across the y-axis. And then we're going to connect those dots. It's going to look something like this here. And so from that, the domain, there's still no variables in the bottom of a fraction. There's still no roots. So the domain is still anything, negative infinity to positive infinity. The range on this one, low to high, we still have, this time it's up 1. So everything that was before got moved up 1. There was originally a horizontal asymptote at y equals 0, but now it's going to be up 1, so it's going to be y equals 1. It's going to be the horizontal asymptote. The range never actually crosses that horizontal asymptote, so the range is going to be from 1 up to infinity, and the horizontal asymptote is y equals 1. A number e is kind of a special number related to growth. It's defined as a number in the expression 1 plus 1 over n all to the n power as n approaches infinity. In calculus, this right here would be, this down here is how we express it, is e is equal to the limit as n approaches infinity of 1 plus 1 over n to the nth power. What this means, or what this kind of comes from, is what happens as something has continuous growth. That's kind of where this comes from. So 1 plus 1 over n as n gets huge, this part right here is going to approach 0, but we're adding 1, so this inside here is always going to be greater than 1, and anytime we have something greater than 1 that's approaching, that has a power that's approaching infinity, we get this number e. And the number e is approximately 2.72. So if you see e, I know it's a letter, but it also represents the number that's approximately 2.72. And we can do e to the x just like before, thinking of e as 2.72. So here we get our graph of y is equal to e to the x, right here. Well, what's it going to look like if we took f of x is equal to e to the x plus 1? So this is the original graph, e to the x. What would I get if I wanted to graph f of x is equal to e to the x plus 1? What does that plus 1 do? That plus 1 is right next to the x. It's in the exponent. That is going to shift the graph either left or right. When it's a plus 1, it actually shifts it the opposite direction. So this is going to shift the graph 1 left. All these points here are going to get shifted 1 to the left, 1 to the left, 1 to the left, 1 to the left. And so when we connect those dots, they're all just going to be 1 unit shifted to the left. It's still going down, still approaching that y equals 0. It's just 1 left. So what's the domain of this? The domain, we can still put anything in. Negative infinity to positive infinity. And the range, it's approaching that horizontal asymptote y equals 0. So the range, it never is going to cross that. It's from 0 up to infinity. And the horizontal asymptote is going to be y equals 0. At this point in the movie, or in the video, what I wanted to do, I wanted to show you what it's going to look like when you're doing this in MyMathLab. So over here in MyMathLab, yes, I want to continue. So here it says use transformations to graph the function, determine its domain, range, horizontal asymptote. Here we have the function. When I go to graph it, I'm just going to click on this, click to enlarge graph, and then I can still see over here is the function that I'm trying to graph. I know it's an exponential, so I know it's going to look something like this here. I click on that. That's what I'm hoping to graph, is an exponential. And then you can actually click, it doesn't really matter, you can click anywhere inside there, anywhere in the graph area, and this is going to come up here. I look at the bottom, the base over here is 5 to the x, so the base, and it's not going to be e, the base is going to be 5, and then minus 1 is a vertical shift, it's down 1, so over here in vertical shift I would go vertical shift, I would go down until it says 1, and I'll slide this off to the side. I'm going to check to see here once. If I were to put 0 into this, 5 to the 0th is 1, 1 minus 1 is 0. So when I put 0 in, I get 0 out. That's good. If I put 1 into here, 5 to the 1st is 5, minus 1 is 4. So 1 in, 4 out. Looks good. I think this is the right graph. I'll go ahead and check it. And excellent. Okay. It's going to ask for some more information. The domain, well, just as a review, the domain can be anything, anywhere from negative infinity to positive infinity. And the range, normally the range is on the, it never crosses the x-axis or the asymptote y equals 0, but this one is shifted down 1, so the range is going to be from negative 1, it's never going to actually equal minus 1, and then up to infinity for the range. The horizontal asymptote, that's the line y equals negative 1. I'll show you what another one would look like. Here we have this function. It's still an exponential. I'm going to click on here. I want to do the exponential. This one looks a little bit different. There's a few less options. So when I click on this, I click somewhere in the graph. This one has this come up. But here, the base, in this case, is 4. So I'm going to change this base to a 4 over here. And then this minus 1 right next to the x, it's not outside of everything, it's right next to the x. That shifts it left or right. So that shifts it left. Nope, the minus 1 shifts it opposite, just opposite, so it shifts it right 1 unit. So for a horizontal shift here, it's going to be 1 unit to the right. And then we'll save that, check the answer. I'm going to get the answer. I can do those other parts, but what I want to take time to do is show you this one right here. This one here, I click on the graph again. It's an exponential. So we have 3 plus 5 to the x over 4. I already clicked on that. Click somewhere in here, this box pops up. My base is the 5. That came from there, right there. This plus 3, it's outside of everything. So that's a vertical shift up 3 to 3. And then this x over 4, when we're multiplying something, or we're multiplying or dividing the x by something, that is a horizontal stretch or compression. So this is a horizontal stretch or compression of 1/4 is what we're, because that's what we're multiplying the x by. So we do all that. Go ahead, save this, check the answer, and there we go. And again, I just wanted to show that to you on MyMathLab so you could actually see what it looks like. Now back to some of these, solving this equation. So we have 3 to the x is equal to 27. This would be the same thing as 3 to the minus x. 27 is 3 to the third, because 3 times 3 times 3, we have 3, 9, 27. In order for these two to be the same, since the base is the same, all that has to happen is the negative x has to equal the 3, or the x would have to be negative 3 if we multiply both sides by negative 1. Another example, this one's a little bit different, but 5 to the negative x is equal to third. So here, there's no way we're going to get the same base between 5 and the 3, not without some really messy decimals. But we have 5 to the negative x is equal to 3. So what's going to be 5 to the 3x? Well, how do we get from 5 to the negative x to 5 to the 3x? This here, we would have to raise this here, because when they have a power raised to power, they get multiplied. So a negative times a negative would give us a positive, and then negative 1 times a negative 3 is a positive 3. We would have to raise this here to negative 3. If I do that to the left side, I have to do that to the right side. Equals 3 to the negative 3. Well, that's exactly what it's asking. What does 5 to the 3x equal? It equals 3 to the negative 3. 3 to the negative 3 is the same thing as 1 over 3 to the third, which is 1 over 27. That concludes this section. I hope this is helpful. Again, if you're looking for a little bit more deeper explanation, a little bit more in-depth, you can always go over to the author and action videos, which are in the chapter contents of MyMathLab.